Have you ever walked into a room and flipped 3 or 4 different light switches before you finally found the one that operated the light you wanted? Have you ever turned on the wrong burner on your stove? Have you ever struggled with setting the alarm on a digital clock? Well, if so, you probably blamed yourself. But in fact, you were simply experiencing the frustration that inevitably results from poor design. Last lecture, I cited the intriguing statistic that each of us is surrounded by approximately 20,000 everyday things. Some of these things have been thoughtfully designed, such that we can easily figure out how to use them without reading an instruction manual or having someone explain how they work. But unfortunately, many have not been so thoughtfully designed. And that's a problem. Not only because few of us have enough time to read 20,000 instruction manuals, but also because poor design can seriously hinder our ability to use these products and devices effectively. Here lies one of the great ironies of our modern high-tech world. Even as myriad new technologies promise to make our lives easier and more fulfilling, their excessive complexity and flawed user interfaces often make our lives more frustrating and can severely limit the potential benefits of these same devices. During this lecture, we'll be exploring the design of everyday things, a subject that draws upon the broader fields of human factors engineering, ergonomics, and engineering psychology. I'll also be drawing extensively upon the work of Dr. Don Norman, an engineer and cognitive psychologist who pioneered the field of user-centered design and has written several well-regarded and highly readable books on the subject. In my view, this is a particularly exciting aspect of everyday engineering because, in the spirit of user-centered design, there's no one better equipped to assess the success or failure of everyday technologies in meeting our needs than we are. We are, after all, the users. So let's begin by examining a very common everyday technology that allows us to experience good and bad design many times a day: the water faucet. And when we use a faucet, we expect it to perform two very specific functions: controlling the water temperature and controlling the rate of flow. In this sense, it's a very simple device, and thus we might reasonably expect to be able to operate any faucet in any place without instructions and without resorting to trial and error. Sadly, this is often not the case. Here's a very common faucet design featuring two knobs, one for hot water, one for cold. When we operate this device, it usually responds as we expect, as long as it's been installed consistent with the unofficial worldwide convention of placing the hot water control on the left and the cold water control on the right. Unfortunately, this convention is sometimes ignored, and when that happens, I'm guaranteed to operate the knobs incorrectly, no matter how well marked they might be. Such is the power of convention in governing our interactions with technology. But there's a larger usability issue with this faucet design. Another common convention is that rotating a knob to control flow should be analogous to turning a bolt. Clockwise rotation tightens a bolt, and thus it should reduce flow. Counterclockwise rotation loosens a bolt, and thus should increase flow. The valves in your plumbing system operate this way. And the convention makes sense, because many such devices actually do use a screw to open and close an internal stopper, as you can see here. Now, according to this convention, both knobs on this faucet should close with clockwise rotation, like this, and open with counterclockwise rotation, like this. The problem is that some manufacturers disagree with this convention. They propose an alternate paradigm that controls intended for two hands should reflect the symmetry of the human body, and thus should operate as mirror images of each other, like this. Well, this concept is quite attractive in theory. But as we engineers are fond of saying, in theory, there should be no difference between theory and practice. In practice, there is. When this mirror image paradigm is applied to a faucet with two knobs, three distinct problems arise. First, we're so conditioned to the traditional convention that when we encounter this alternative convention, we'll invariably turn one knob or the other in the wrong direction on the first attempt. Second, even if we're expecting the mirror image paradigm, there's no clear convention for which direction is on and which direction is off. So we'll still get it wrong on the first attempt about half the time. And most important, a design that's optimized for two hands breaks down entirely when we operate it with one hand. Imagine that you're taking a shower, you've got a bottle of shampoo in your right hand, you've got soap in your eyes, the water temperature is a bit too low, and so you reach across to adjust the cold water knob with your left hand. What's the chance that you're actually going to turn it in the correct direction? Applying the mirror image paradigm to faucet knobs is unequivocally bad design, particularly because the inherent flaws in this paradigm can be so easily corrected. This faucet uses the mirror image paradigm, but its mode of operation is crystal clear, thanks to the simple substitution of handles for knobs. When the faucet is shut off, the handles are both pointed outward, a clear signal that the mirror image paradigm is being used. It's also clear that both handles must be rotated forward to turn the water on because there isn't enough clearance behind them to allow rearward rotation. Furthermore, the shape of the handle sends a subtle message that they're to be grasped and pulled, further reinforcing our intuition about how they should work. For all these reasons, it's nearly impossible to operate this faucet incorrectly. Yet another advantage. With the water running, the position of the handles provides a visual indicator of the state of the system. Here, for example, we can instantly see that the stream of water is mostly cold with just a little bit of hot. Knobs don't provide this sort of real-time visual feedback. A faucet handle is so effective at communicating how it's supposed to be operated that it even works when it's misused. This faucet uses the traditional clockwise closed, counterclockwise opened convention, but the building maintenance crew evidently ran out of knobs and installed levers instead. It looks absolutely ridiculous, but it's perfectly usable. We have no difficulty deciding which way to rotate the handles to operate this device. Now, these examples illustrate three important points about design for usability. First, the difference between poor design and good design can be quite subtle, but the effects are often dramatic. Second, solely by virtue of their shape, size, and placement, physical objects send us subtle messages about how they can or should be used. These messages are called affordances. And high-quality design invariably takes advantage of affordances to improve the interaction between technological devices and people. Finally, physical limitations or constraints can also communicate how a device should or should not be used. Positioning these handles so they couldn't possibly be rotated in the wrong direction was a very clever use of constraint by the designer. Now, its effectiveness notwithstanding, our mirror image handles aren't perfect. Recall that the two functions we expect of a faucet are control of temperature and control of flow rate. The two controls on this faucet don't address either of these functions directly. Indeed, to achieve either function, we usually have to operate both controls simultaneously. Controlling the temperature is particularly problematic because the only way to test whether we've achieved the correct mixture of hot and cold is to place a hand into the stream of water, even as we need both hands to make the adjustments. Moreover, once we've got the temperature right, increasing or decreasing the flow rate without inadvertently changing the temperature is nearly impossible. This faucet attempts to address these issues by providing a single handle to control both functions. The handle moves both side to side for temperature control and front to back for flow rate control. In the side-to-side direction, left corresponds to hot and right to cold. So far, so good. But the flow rate control is more problematic because it's not clear which direction should correspond to greater flow and which to less. With some single-handle faucets, we pull the handle toward us to turn the water on. And this makes sense because the forward-downward movement of the handle corresponds logically to the downward flow of the water. But with other models, we lift up on the handle to turn on the water. And this makes sense too, because we tend to associate up with on and down with off. What we have here is a mapping problem. The association between a control and its associated action is ambiguous. Effective designs address this ambiguity with affordances and constraints. Note how on this faucet, the handle is nearly horizontal and relatively close to the spout when the water isn't running. There isn't enough room to push it downward, so it's fairly obvious that we need to lift it up to turn on the water. A well-designed single-handle faucet is functionally superior to any faucet that uses separate controls for hot and cold water because the configuration aligns more closely with the functions we expect from this device. The single-handle design also has a much improved feedback mechanism. I can operate the control with one hand and feel the temperature of the water with the other. But it's still not perfect because the merging of two functions into a single control often makes it difficult to perform one function independently of the other. And the whole system falls apart in cases like this one, where the spout can rotate from side to side, and thus it no longer provides a point of reference for the middle of the handle's temperature range. Well, one way to avoid problems associated with controlling two functions simultaneously is to eliminate one function entirely. It's a fairly drastic approach, but it's used. There are two categories of faucets designed to do just that. The first, typically found in public restrooms, uses a fixed temperature and allows only the flow rate to be controlled. The other, common in hotel showers and recently in residential construction, uses a fixed flow rate and allows only the temperature to be controlled. Both systems are typically used to limit water consumption. They are most definitely not designed for usability. If you were around when fixed temperature fixtures were first introduced in public restrooms, you probably had the same experience I did. You encountered a faucet, like this one, with a single knob, and you did what you'd been doing to knobs for your entire life. You gave it a twist, and nothing happened. Eventually you figured it out, maybe through trial and error, or maybe by observing someone else who had already figured it out, or maybe you noticed the subtle word push embossed into the top of the knob. And then, if you're like me, you probably felt foolish. But there was no reason for any of us to feel foolish. As Don Norman insists, anytime written instructions are required to operate a device as simple as a water faucet, the fault lies with the design, not with us. Little did we know, it was only going to get worse. Just about the time we figured out how to push the button, along came hands-free faucets, like this one, which use a proximity sensor to detect the presence of your hands and then turn on the water for a programmed interval of time. In many ways, the hands-free faucet actually makes good design sense. To activate it, we place our hands exactly where they need to be, in the sink, and we avoid manipulating physical controls that have been handled by many other people in a relatively unsanitary environment. But as you've certainly experienced, hands-free faucets and hands-free soap dispensers and hands-free paper towel dispensers can be maddeningly user-unfriendly. The first challenge is simply recognizing that the device is indeed hands-free. How many times have you waved your hands repeatedly in front of a paper towel dispenser only to realize that it's actually a manually operated machine? On a recent trip to Europe, I visited a public restroom and spent considerable time trying to elicit water from this hands-free fixture, to no avail. I had given up in frustration when the guy next to me said something in Italian, and then he pointed to this foot pedal below the sink. So this was a hands-free sink, but not the type I was expecting. The most common design flaw in hands-free devices is that they lack clear indicators of where the proximity sensor is and how we should interact with it. In Don Norman's lexicon, they lack signifiers. Here's a particularly egregious example. When I arrived at this sink, I put my hands here, thinking that this metal fixture was a water spout, and therefore the proximity sensor must be immediately below it. I was aided in this misperception by the drain immediately below. After some time, that familiar feeling of embarrassment set in, and I realized that the metal fixture is actually a manually operated soap dispenser. So I reasoned, the water spout must be underneath this shelf, and this black oval must be the sensor. Well, after more fruitless hand-waving, I eventually determined that the black oval isn't a sensor after all, it's just a bit of decoration. Both the sensor and the spout are underneath this shelf, completely hidden from view. And only after I finally succeeded in eliciting water from that hidden spout did I realize that my trials and tribulations had also been exacerbated by a considerable time lag between the activation of the sensor and the flow of water. A feedback issue that's all too common with these evil devices. The sink is the quintessential example of the pitfalls inherent in pursuing style over substance. It looks beautiful, modern, sleek, and uncluttered. But from the perspective of usability, it's a total disaster. So, what about those fixed flow rate shower fixtures that control only temperature? Recently, we've seen increased use of this control, a simple handle that rotates from off to cold to hot. This mapping between rotation and temperature isn't especially logical or natural, so the operation of the control is invariably aided by a signifier like this one. But the great flaw in this design is that off is located only at one extreme of the handle's rotation. When it's time to shut off the water, we don't want to get hit with a burst of cold water, so we need to turn the handle very quickly. But if we've forgotten which direction is off, we're quite likely to get scalded. Still, I have become quite familiar and comfortable with this style of temperature-only shower control, probably because I've encountered it so often. But familiarity with a particular design paradigm often leads to frustration when we encounter a different one, even just a slightly different one. Recently, I stayed in a newly constructed hotel that was equipped with this shower fixture. Preparing to take my shower, I gave the handle a counterclockwise twist, and nothing happened. After messing with it for a few moments, I gave up, quite convinced that the shower wasn't working. When I complained to the desk clerk about this particular shower, he responded impatiently, as if he'd received this question many times. "You have to pull," he said. Well, I was so incredulous that I walked all the way back to my room just to determine if I really could be that clueless. And indeed, I was. Not only did pulling the handle turn the water on, it also actually controlled the flow of water quite effectively. And rotating the handle controlled the temperature as expected. The irony is that of all the different faucet configurations I've encountered, this one is probably most effective in that it allows for direct, precise, independent control of both functions, flow rate and temperature. In retrospect, I can also see that the designer even gave me a subtle hint about the dual function control. This double-ended handle has affordances suggesting both rotation and pulling. But I failed to catch the hint, and ultimately the design failed for lack of clear signifiers communicating how it was supposed to be operated. Okay, at this point, you're probably starting to wonder about my apparent fixation with faucets in public restrooms and hotels. But I can assure you, my advocacy for high-quality design extends to all aspects of everyday engineering. I've only chosen to focus on faucets in this lecture because they provide particularly clear illustrations of basic design principles in a context that's quite familiar to all of us. So what are these principles of design? Don Norman has formulated 5 of them, and we've already seen all 5 illustrated, some positively, some negatively, in the water faucets that we've been examining. All 5 rules reflect the importance of discoverability, a set of characteristics that communicate what actions are possible and how they're to be performed. Designers achieve discoverability through thoughtful incorporation of affordances, signifiers, mapping, constraints, and feedback into their designs. Let's review these terms and discuss them in a bit more depth. An affordance is a message conveyed by the physical configuration or placement of an object about how people can interact with it. An affordance is both a physical property and a perception by an individual human. So discerning affordances can be somewhat subjective and it can be culture dependent. Nonetheless, many affordances are nearly universal. Knobs afford turning and pulling. Handles afford pulling. Flat plates and crash bars afford pushing. You won't have any difficulty negotiating these three doors because their affordances clearly communicate how they are to be used. This door is another story entirely. It has identical handles on both sides, even though it must be pushed from one side and pulled from the other. Because a handle always affords pulling, most people will instinctively pull when they're supposed to push, and the simple act of walking through a door will take 2 attempts. This is poor design, a fairly common characteristic of high-style glass doors, which too often reflect excessive emphasis on form over function. Here's a similar example on a low-style door. And you can bet that the push sign was posted because so many people were trying to open these doors by pulling on the handles. On this door, the word push is a signifier, an explicit message about how the object is to be used. Too often we see signifiers that are needed to compensate for the designer's failure to use affordances effectively, as we see in the push sign example, and as with this use of large red dots to prevent people from walking into these glass doors. But signifiers are far more effective when they're used to augment or enhance natural affordances to improve understandability. The knob on this fan affords turning, but the signifiers on the knob provide the additional information that 3 different speed settings are available. Next, mapping, the relationship between controls and the actions they control. The best mappings are natural mappings, which take advantage of physical, spatial, or logical analogies. For example, moving a control upward to raise the level of illumination, or moving a control forward to initiate forward motion. Natural mappings almost always lead to understanding. Poor mappings usually lead to frustration and error. This common linear arrangement of controls on a stove is poorly mapped because it doesn't distinguish between front burners and back burners. As a result, these signifiers are typically added to compensate, but just a slight adjustment to the arrangement of the knobs would do this job far more effectively. This is the floor plan of my kitchen. On this wall is a row of 6 identical light switches. When I flip these switches in order from left to right, the following lights are illuminated. 1, 2, 3, 4, 5, 6. Note that there is no spatial logic to this arrangement whatsoever. And so, even though I've lived in this house for over 2 years, I still select incorrect switches several times a day. Recognizing that poor light switch mapping is a big systemic problem, Don Norman has developed this fundamentally new concept, an angled panel that displays the floor plan of the room with switches placed in the locations of the lights they control. This is a beautiful design, but thus far it hasn't drawn much attention from either the lighting or the construction industries, probably because it represents such a radical departure from the status quo. Next, constraints are physical limitations that communicate how a device can or can't be used. The 3-prong plug is a superb example. It's physically impossible to insert this thing into a wall socket in any orientation other than the correct one. A less successful example is the universal serial bus, or USB plug, that's used to connect peripheral devices to your computer. The USB is successful because the plug will only fit into a USB receptacle in the correct orientation. But it's not entirely successful because the correct orientation is rarely obvious, particularly when the receptacle is oriented vertically. And finally, our interactions with technology are greatly facilitated by responsive, meaningful feedback. When I press an elevator call button and it lights up, I'm satisfied that an elevator is on the way. But when I press this button at a pedestrian crosswalk, and there's no visible or auditory confirmation that my input has been received, I get increasingly frustrated as time passes. Fairly soon, I begin to doubt whether the system is even working, and at some point, I might even ignore the do not walk signal and cross the street, risking personal harm. Feedback promotes the effective use of technology. Lack of feedback often discourages it. These are Don Norman's principles of good design. And while I've tried to illustrate them with simple examples, like doors and plugs, they're equally applicable, and perhaps even more useful, for more technologically advanced devices, like programmable coffee makers and computer user interfaces. You might be wondering why standardization isn't on Norman's list. After all, if there were one worldwide standard for faucet design, I wouldn't have experienced all the trials and tribulations I recounted earlier in this lecture. The answer is that standardization certainly has its place, but usually as the design strategy of last resort. In a world of so many diverse interests and agendas, standardization is extremely difficult to achieve. And once it has been achieved, widespread adoption often guarantees that the standard will outlive its usefulness. As evidence, we need look no farther than our computer keyboards, which still use the arrangement of keys that was optimized for the mechanical typewriter. More importantly, if a device is designed for discoverability, standardization usually isn't necessary. Now, once you've internalized Norman's principles, I suspect you'll begin noticing many examples of both good and bad design in the everyday technologies that surround you. But why is poor design so incredibly persistent? In a consumer-driven economic system like ours, one might expect that market forces would drive manufacturers to pursue improved usability aggressively to gain a competitive edge. Yet often they do not, for four reasons. First, as we've seen with high-style glass doors and faucets, the design community sometimes places greater value on aesthetics than on functionality. On some level, we contribute to this problem when we tolerate poor usability because the design just looks really cool. Second, many technologies are designed by engineers whose worldview is dominated by how the device works rather than how people interact with it. Third, designers often work for someone other than the end user of the product. For example, most light switches are sold to electricians and contractors rather than to homeowners. Thus, the designer of light switches is more likely to be influenced by installation issues than by usability issues. Most importantly, in product design, the competitive marketplace tends to favor the introduction of splashy new features over the thoughtful refinement of existing ones. Getting usability right requires thoughtful refinement. And while splashy new features might make a product appear more desirable, they often add complexity that substantially reduces the product's usability. Does this blender really need 16 speeds? And on this microwave, what does the breakfast button do anyway? What in the world is an inverter defrost? And why do I need it? So, is there anything we can do about bad design? Well, yes. Don Norman's research suggests that designers and manufacturers do pay attention to usability when they believe it will improve their bottom line. Thus, we can make usability matter by applying principles of good design to evaluate the everyday technologies we own, and then using online ratings to send the message back to their manufacturers. Most importantly, we can make usability a primary criterion for all the things we buy. And then, Even if we don't succeed in changing the world, we'll still surround ourselves with well-designed products that enable us to achieve our goals more fully with considerably less frustration. For the next 4 lectures, we'll be departing from the comfortable, well-appointed world of your home's living space and entering the austere and occasionally greasy environment of your garage to explore the major technological systems that constitute your automobile. Automotive technology has an immense influence on our everyday lives. When our cars are working as designed, they provide us with nearly unlimited mobility. And when they aren't, well, few events are more disruptive to our everyday lives than an automotive breakdown. Automobiles are among the most expensive products we purchase. Yet, our ability to make these purchases wisely is often hindered by the bewildering array of functional, aesthetic, and technological alternatives available in the marketplace. In a broader sense, the automobile has also had profound influences on our society, culture, economic development, land use, and environment. Some of these influences have been extraordinarily positive, others dangerously detrimental. All of them derive, at least in part, from the nature of the technology itself. For all these reasons, it's very much in our interest to know more about these machines and how they work. During this lecture, we'll examine the technological system that has been the foundation of automotive engineering since its inception, the internal combustion engine. Then, over the following 3 lectures, we'll look at the automobile's other major components, the drivetrain, suspension, steering, and braking systems. Along the way, we'll do our best to view these components not as independent entities, but rather as beautifully integrated elements of an elaborate system of systems that has been continuously updated and refined for well over a century. The internal combustion engine is a machine that converts chemical energy in a hydrocarbon fuel into the mechanical energy of a rotating shaft. There are 2 basic types. Spark ignition engines generally run on gasoline, while compression ignition engines run on diesel fuel. Today we'll focus primarily on spark ignition, though we'll also touch briefly on compression ignition, if only to clarify the differences between these 2 systems. At the heart of both systems is a chemical reaction involving the combustion of a hydrocarbon fuel. You might remember from the lecture on coal, oil, and natural gas that a hydrocarbon molecule is a chain of carbon and hydrogen atoms. Gasoline is composed of over 100 chemical compounds. A typical example is the hydrocarbon we've all heard of, octane, which has 8 carbon and 18 hydrogen atoms. And here's the chemical reaction associated with its combustion. In a spark ignition engine, octane combines with oxygen from the air to produce carbon dioxide and water. This chemical reaction is exothermic, meaning that it also produces energy. And it's this energy that ultimately propels your car. The combustion reaction takes place within cylindrical cavities that have been machined into a solid block of iron or aluminum, called the engine block. These cavities are called cylinders, and they're just large enough to accommodate metal pistons sliding up and down within them. Near the top of each piston are several grooves, which hold metal rings that provide a tight seal between the piston and the cylinder walls. Pistons are hollow and open on the bottom to facilitate their pinned attachment to connecting rods, which link each cylinder to this crankshaft. As this photo of an upside-down engine block shows, the crankshaft is mounted within the bottom of the block in an enclosure called the crankcase. When the engine is assembled, the crankcase is closed off on the underside by the oil pan. And here's how it all works. The up and down or reciprocating motion of the pistons is translated by the connecting rods into rotational motion of the crankshaft, which then delivers mechanical power to the vehicle's drivetrain, the subject of our next lecture. The distance each piston moves within its cylinder is called the stroke, which extends between this position, called top dead center, and this one, bottom dead center. When the engine is running at normal operating speeds, the cylinders are cycling up and down many thousands of times per minute. And because the mass of each cylinder must be accelerated from a dead stop at the start of each stroke, the engine's efficiency is enhanced by keeping the cylinders as light as possible, and that's why they're hollow. Each cylinder is equipped with an intake valve, an exhaust valve, and a spark plug, all of which are mounted within a heavy metal lid called the cylinder head. As this cutaway of a cylinder head shows, the two valves are used to close off intake and exhaust ports, which are cast directly into the head. Now, we'll discuss many more components of this engine shortly, but these, the cylinder, piston, connecting rod, crankshaft, valves, ports, and spark plug, are the ones that are directly involved in the process of producing mechanical power. So for now, let's focus on this process. Most automobile engines operate on a 4-stroke cycle, meaning that each piston moves through a sequence of 4 different strokes, each with a specific purpose, and this 4-stroke sequence is then repeated over and over again for as long as the engine is running. We'll begin by examining the 4-stroke cycle for an engine with a simple carburetor, and then a bit later, we'll see how it works with the carburetor's modern replacement, fuel injection. The first of our 4 strokes is the induction stroke, during which the piston moves downward in its cylinder and the intake valve opens. A mixture of fuel and air is drawn from the carburetor through the intake port into the cylinder, and then the valve closes. Now, during the compression stroke, the cylinder moves back upward. Both valves remain closed, so the fuel-air mixture is now compressed and its temperature increases simultaneously. Just before the cylinder reaches top dead center, a pulse of high voltage is sent to the spark plug, causing an electric arc to jump the gap between these 2 electrodes. This is essentially the same phenomenon we identified as flashover in our lectures on electric power transmission and distribution. Within the cylinder, this electric arc ignites the compressed fuel-air mixture in the cylinder, initiating the combustion reaction we discussed earlier. The resulting heat causes a very rapid increase in pressure, which drives the piston back downward, and this is the power stroke. Finally, during the exhaust stroke, the exhaust valve opens, and the piston moves back upward, expelling the cylinder's contents into the vehicle's exhaust system. These contents include the 2 byproducts of the combustion reaction, water and carbon dioxide, plus a lot of nitrogen, a major constituent of the air originally introduced into the cylinder. The exhaust also includes a small amount of pollutants, unburned fuel, carbon monoxide, which is produced by incomplete combustion, nitrogen oxides, produced by the unintended reaction of nitrogen and oxygen, and soot. We'll see what happens to this stuff when we discuss the exhaust system shortly. Note that in the 4-stroke cycle, each stroke corresponds to 1/2 rotation of the crankshaft, but power is produced during only 1 stroke. So what keeps the piston moving up and down during the other 3 strokes? Why, the other pistons, of course. This is the principal reason why most automobile engines have 4 or more cylinders. The 4-stroke cycles of the cylinders are staggered, such that each has its power stroke at a different time. Cylinders can be arranged in these 3 different configurations: inline, V, and horizontally opposed. Note that in each case, the firing order is designed such that power strokes from different cylinders are delivered at different times. So the intake, compression, and exhaust strokes for a given cylinder are driven by the power strokes of the other cylinders. Note also that the motion of the pistons is always balanced. At any given moment, half of the pistons are moving upward or outward, and the other half are moving downward or inward. If they weren't balanced in this way, the engine would vibrate tremendously. The alternating motion of the pistons is controlled by the crankshaft, which has three important characteristics worth noting. First, these offset sections of the shaft, called crank pins, are the mechanism by which the reciprocating motion of the pistons is converted to the rotary motion of the shaft. In this sense, the crankshaft really works like any other crank. This model illustrates how a simple crank converts rotary motion into the reciprocating motion of a piston through a connecting rod. The system works in the other direction as well, like this. But note that it doesn't really work as well, because the piston tends to get stuck either at top dead center or at bottom dead center, where vertical movement of the piston won't turn the crankshaft. This is another reason why automobile engines have multiple cylinders, so each cylinder can have its power stroke in the position where the resulting torque is maximized, like this, and when it's in this position, bottom dead center, a different cylinder will keep the crankshaft moving, like this. The second important characteristic of the crankshaft is that it incorporates counterweights, like these, which balance the offset weight of the crank pin to reduce vibration. And third, the crankshaft always incorporates a flywheel, a heavy wheel fixed to the end of the shaft to smooth out the discrete pulses of torque that are delivered to the shaft intermittently by the individual pistons. We'll discuss the flywheel in greater detail in the next lecture. By the way, the number and arrangement of cylinders used in an engine is based on a couple of factors. Using more cylinders generally produces a smoother running engine, but also causes greater complexity. And the V and opposed configurations result in a more compact engine for a given number of cylinders. Thus, inline six-cylinder engines used to be quite common, but today they've almost been entirely replaced by V6s, which fit more comfortably in the engine compartments of smaller cars. Well, we've now seen the four-stroke cycle in action, but it's important to recognize that we've only really seen it in slow motion. In an engine running at 4,000 revolutions per minute, the complete four-stroke cycle occurs 2,000 times per minute, or 33 times per second. That's one full cycle of induction, compression, power, and exhaust every 3/100ths of a second. With that in mind, you might be wondering, how are the valves opened and closed with such precision? How is the correct air-fuel mixture introduced into the cylinder during the induction stroke? How does the spark plug fire at just the right moment to initiate the power stroke? How are all those combustion products removed from the automobile, and how are the fumes made safe enough to be released into the atmosphere? How is the heat from thousands of explosions per minute dissipated from the engine block? How is the sound from thousands of explosions per minute controlled? And how are all those moving parts lubricated to keep them working freely and prevent excessive wear? The answers to these questions can be found in 7 additional engineered subsystems of the internal combustion engine: the valve train and the fuel, electrical, ignition, exhaust, cooling, and lubricating systems. Every one of these subsystems must operate in perfect synchronization, or the engine simply won't run. Let's look at each of them, starting with the valve train. This is a typical automotive valve called a poppet valve. It consists of 2 elements, a disc and a long stem. Here's a cutaway of a cylinder head showing the intake and exhaust valves associated with a single cylinder. The cylinder itself isn't shown, but would be located down below the valves. Now note that the 2 valves are seated in the openings of the intake and exhaust ports, with their stems extending up through the head. Each valve is held shut by a strong spring and opened by that odd-shaped component immediately above called a camshaft. This is a model that illustrates how a camshaft works. Now, in general terms, a cam is an irregularly shaped lobe, like this one, that's used to convert rotational motion into linear motion. Let's give it a try. Note that as the camshaft rotates, the projecting lobe on each cam depresses a particular valve stem at the appropriate time. After the lobe passes, the spring returns the valve to its closed position. Each cam is oriented in a different direction, so as the shaft turns, the valves all open at different times. And if you find this noise as annoying as I do, well, suffice it to say that this is why real automobile engines are made of metal, not of wood. In most modern engines, camshafts are mounted above the cylinders in one of the two configurations shown here. On the left is a single overhead camshaft engine, with one camshaft activating 2 valves per cylinder through these rocker arms. On the right is a dual overhead camshaft engine with 2 camshafts driving 4 valves per cylinder directly, without rocker arms. This latter configuration is used for high-performance engines where the 4 valves, 2 intake and 2 exhaust, provide increased power by enhancing airflow into and out of the cylinder. In either case, the camshaft is rotated by a belt or chain called the timing belt or timing chain, which is driven by the crankshaft. These drive sprockets are sized such that the camshaft rotates once for every 2 rotations of the crankshaft. Thus, each rotation of the camshaft corresponds to 1 4-stroke cycle. Next, the fuel system. Until the 1980s, most spark ignition engines used a carburetor to achieve the correct fuel-air mixture to support the combustion in the cylinders. In a carbureted engine, outside air is drawn through an air filter into the body of the carburetor, which has this narrow throat at its center. Here we see another application of Bernoulli's principle, which we first discussed in the context of wind flowing over a building. Bernoulli tells us that when air flows through this throat, called a venturi, its speed increases and its pressure decreases. At the point of lowest pressure, a small tube is connected to a fuel reservoir called the float chamber. Because of the low pressure in the venturi, a calibrated stream of fuel is sucked from the float chamber into the airstream. Below this throat is a rotating gate, the throttle valve, which is mechanically connected to the driver's accelerator pedal. When the pedal is depressed, the throttle valve opens and the flow of fuel and air into the engine is increased. The fuel-air mixture passes from the carburetor to an intake manifold, which divides the flow equally among all the cylinders. Now, carburetors haven't been used in automobiles since 1990, but they're worth knowing about because you're still likely to find one on your lawnmower or snowblower. But for today's automotive fuel systems, the name of the game is fuel injection, which provides more power, better fuel economy, and better emission control. In the most common form, called multi-port injection, fuel is supplied by devices called fuel injectors, 1 per cylinder, which spray fuel into each intake port just above the valve, as shown here. The car's fuel pump supplies the pressurized fuel to each injector, which squirts a controlled quantity of fuel through a tiny nozzle in response to commands from the vehicle's computer, the Engine Control Unit, or ECU. The ECU monitors the throttle position and the amount of oxygen in the exhaust to determine just the right amount of fuel to deliver at any given time. Because multi-port injection supplies fuel upstream of the intake valve, the operation of the 4-stroke cycle in a multi-port injected engine is essentially identical to that of a carbureted engine. However, some high-performance gasoline engines and most diesel engines use direct injection of fuel right into the cylinder. In these engines, the induction stroke draws in only air, and the fuel isn't injected until near the end of the compression stroke. This allows the fuel to be injected at higher pressure, resulting in a finer mist that greatly improves the combustion process. Now let's examine the ignition system that puts the spark in your spark plugs. Your automotive electrical system is powered by an alternator, which is really just a belt-driven generator that receives shaft power from the crankshaft and converts it into electrical power. Normally, the alternator supplies power for all of the vehicle's systems while the engine is running, and it also charges the battery. The battery provides power when the engine is shut off, most importantly for cranking the starter. The battery supplies power at 12 volts, but spark plugs require tens of thousands of volts to create that electrical arc that initiates combustion. Until recently, most automotive ignition systems provided this immense voltage boost with a device called the coil, essentially a transformer consisting of two sets of windings on an iron core. The primary winding has relatively few turns of wire, and the secondary winding has many thousands. The primary winding is energized by the battery through a rotating switch called the contact breaker. As this current is periodically switched on and off, the resulting change in the coil's magnetic field induces the required high voltage in the secondary coil, which is connected to the distributor. True to its name, the distributor's job is to distribute power to each of the spark plugs in the correct firing sequence. This device contains a rotor, which is driven by the camshaft, so its rotation is synchronized with the four-stroke cycle. High voltage power from the coil enters the rotor through a connection at the center of the distributor cap, and it's passed to output contacts around the circumference of the distributor. Each of these contacts is connected to a spark plug wire. Thus, as the rotor spins, it sends a high voltage pulse to each plug, just in time for the power stroke in the associated cylinder. In modern engines, the single coil and distributor have been largely replaced by an alternative configuration that performs the distribution function electronically at low voltage, and then uses a separate coil for each cylinder to boost the voltage immediately ahead of the associated spark plug. The result is significantly better control over the timing of the spark, which improves power, fuel consumption, and emission control. And because distributors normally wear out relatively quickly, these distributor-less engines require significantly less maintenance. While we're on the subject of ignition, I should mention that compression ignition, or diesel engine, works essentially the same way as the spark ignition engine, except that it has no spark plugs, and relies instead on spontaneous combustion of the fuel-air mixture at very high pressure. Thus, in a diesel, the induction stroke draws in only air. The compression stroke achieves significantly higher pressure and temperature than would be the case in a spark ignition engine. Fuel is injected directly into the cylinder near top dead center, and combustion occurs spontaneously, without an externally supplied spark, as soon as the fuel is injected. And if you don't believe that a flammable material can burst into flame solely through the application of pressure, remember what happens to a piece of tissue paper when I compress the air in this cylinder. In general, diesel engines provide more power and better fuel economy than the equivalent spark ignition engine. However, because they operate at higher pressure, they must be significantly heavier, and so they're usually used for larger vehicles like trucks and locomotives. Whether for a gasoline or diesel engine, the automotive exhaust system typically consists of an exhaust manifold, which collects up the combustion products from the cylinders, a catalytic converter, which substantially reduces the amount of carbon monoxide, nitrogen oxides, and unburned hydrocarbons in the exhaust stream, a muffler, which dampens the sound of those thousands of explosions per minute occurring in the cylinders, and a tailpipe, which routes the exhaust stream out into the atmosphere. To do its work, the catalytic converter requires oxygen, and so the system includes sensors that monitor the amount of oxygen in the exhaust stream. If it's inadequate, the engine control unit increases the quantity of air entering the engine. The internal combustion engine also includes elaborate systems for lubrication and cooling. A reservoir of lubricating oil is contained in the oil pan, which encloses the underside of the crankcase. An oil pump, driven by the crankshaft, draws oil from the sump, passes it through a filter, and then circulates it at high pressure through a maze of channels and passages to every moving part in the engine. After doing its job, the oil trickles back down into the oil pan, where the cycle begins anew. Now, over time, the oil does get contaminated, primarily by tiny particles of metal resulting from the abrasion of the many metal parts that move in contact with each other throughout the machine. And that's why your oil and filter need to be replaced periodically. In the cooling system, a mixture of water and antifreeze is pumped through a network of passages in the engine block to carry heat away from the cylinders. This coolant is then circulated through the radiator, which is really just a heat exchanger, similar to the ones we've seen in your home's heating, ventilating, and air conditioning system. A fan blows across the radiator to assist with the transfer of heat from the coolant into the atmosphere. And that, my friends, is the internal combustion engine in all its glory. Now that we've seen how this beautifully integrated system operates, I'd like to spend a few minutes exploring the science underlying the four-stroke power cycle at its heart. Now, you'll recall that earlier in the course, we were able to glean important insights about refrigeration by modeling it as a thermodynamic cycle, represented as a series of four thermodynamic processes plotted on a graph of pressure versus volume. We can do the same for internal combustion, subject to an important caveat that I'll discuss next lecture. The result, shown here, is called the Otto cycle, named for the 19th century German engineer Nikolaus Otto, who built the first working four-stroke engine in 1876. I swear I'm not making this up. The Otto engine was invented by a guy named Otto. In the Otto cycle, the thermodynamic system is the air contained within one cylinder of the engine. On our graph of pressure versus volume, the cycle begins at state 1, which represents atmospheric pressure, and the volume of the cylinder with the piston at bottom dead center. Process 1-2 is the compression stroke, reflecting a simultaneous increase in pressure and decrease in volume, with the volume at state 2 corresponding to the space above the piston at top dead center. Process 2-3 represents the sharp rise in pressure occurring with the combustion of the fuel-air mixture. Given that the volume is constant during this process, we can see that the Otto cycle assumes that the process occurs instantaneously with the cylinder at top dead center just before the power stroke begins. Process 3-4 represents the actual power stroke, with its corresponding decrease in pressure and increase in volume. And finally, process 4-1 represents the rejection of heat from the cylinder during the exhaust stroke. And, as should be the case with any thermodynamic cycle, we're back at state 1 where we began. Now, in addition to helping us visualize the thermodynamic processes that occur many thousands of times per minute in an internal combustion engine, the Otto cycle also allows us to gain some important insights about engine performance. These insights derive from the fact that for a fluid in a confined space, pressure acting through a change in volume does mechanical work. Thus, pressure times change in volume equals work. We can prove this to ourselves with a simple dimensional analysis. Recall that work is expressed in units of force times distance. Pressure is expressed as force divided by distance squared, and volume as distance cubed. Thus, when we multiply pressure by volume, we get units of work. This mathematical relationship can be represented graphically on our pressure-volume diagram of the Otto cycle. If pressure times change in volume equals work, then the work done during each process of the cycle is simply the area under the associated curve. Thus, the area under process 1-2 is the amount of work input required for the compression stroke. In other words, this is the work done by the engine's other cylinders on the single cylinder we're representing in this graph. The area under process 3-4 is the amount of work output due to the power stroke. There's zero area under processes 2-3 and 4-1 because there's no volume change. So we know these processes do no work at all. And because the net work done by this cylinder is the work output minus the work input, we can visualize the net mechanical work done by one piston during one four-stroke cycle as this area minus this area leaving us with the area enclosed within the Otto cycle loop. This is an extraordinarily important result. As we'll see next lecture, the work done by a piston is directly proportional to the torque delivered to the crankshaft, and as you already know, work per unit time is power. Thus, the two most important characteristics of an automobile engine, its torque and its power, are directly related to this area enclosed within the pressure-volume diagram of the Otto cycle. As such, we can increase torque, increase power, and improve efficiency, all by adjusting the shape of this graph. In the next lecture, we'll explore this concept more fully. And then, once we've gained a thorough understanding of the power produced by an internal combustion engine, we'll figure out how to get that power from the crankshaft to the drive wheels through another mechanical marvel, the automotive drivetrain.